In this video, we're going to look at two questions on the topic of circular motion. Okay, so for the first question, it says an aeroplane flies due east along the equator at a constant low altitude and constant speed relative to the ground. On the aeroplane, a 1 kilogram mass is suspended on a spring balance and records a weight of W1. The aeroplane then flies due east along the equator at the same altitude and speed and measures the balance reading of W2. If the speed of the plane relative to the ground is 250 meters per second, calculate the difference in apparent weights. Okay, so let's look at a diagram first. So let's say this is Earth, and then the aeroplane is rotating around Earth with a speed of 250 ms minus 1. Now, what happens is that the Earth is also spinning on its axis. So in this case, what happens is that, let me draw an enlarged diagram over here. So let's say some kind of spring balance. I won't draw the spring. So this is the balance, and then this is the weight on it. And the plane is moving at 250, and the ground, well, the ground is spinning. Let's say for W1, Earth is spinning this way, and so therefore, what is happening right now is that it will also experience a centripetal force, because essentially it's the plane is essentially rotating around Earth with a certain speed. Now, in this case, the speed of the Earth is essentially the speed at this very instant that is moving this way. Let's say it's VE, and so the exact speed of the plane would be equal to VE plus 250. So now it will actually be a difference in the weight. It's because there's two forces acting on it right now. The first force is its own weight. It's its own weight, and also there's another force that is centripetal force that acting upwards. So let's say W1 will be equal to its own weight. Let's say it's W0 minus FC. And so then we can resolve for it. And for W1 it says in the question it's 1 kilogram mass. So 1 times 9.81 is 9.81. So W0 is essentially 9.81 newtons. Now for FC, in order to resolve for FC, we have to consider two effects: the effect of the plane traveling by itself and the spinning of the Earth. So well, the equation that we can use is v squared over r. And well, my idea is that if we do it completely in this way, then we have to resolve for VE, which will be a rather unnecessary process, because what we can do is that for this part of the equation, we say V is 250, and we can say it's plus by another effect of the Earth spinning, which is 4 pi squared over t squared times r. In this case, we won't need to resolve for VE. We can directly input 1 day into t. Okay, now we can resolve for FC easily. So now it's 250 squared over r. R is given as the radius of Earth, which is 6.37 times 10 to the 6, plus 4 pi squared is over t squared. Now For 1 day, it's 24 times 60 squared to get into seconds squared, and times r, which is again this. Now all we have to do right now is simply input all of these into a calculator. So this will be 250 squared over 6.37 times 10 to 6 plus 4 pi squared over 24 times 60 squared times 6.37. Oh, what happened? Okay, and then 6. Okay, and the answer will be, well, it's quite a small answer. Did I do something wrong? No, I don't think so. Okay, let's just get along with this answer first. Okay, and so the force will be 0.0435, three significant figures. Now, newtons. So in this case, then we can calculate W1. So W1 will be equal to 9.81 minus 0.0435, which is equal to say 9.767 newtons. And then we can resolve for W2. So for W2, let me do over here. W2 is the same concept, so it's W0 minus FC. Now, in this case, W0 is still 9.81, and however FC has changed. So in this case, the VE is essentially going this way. So if it's going this way, then it will be rather different because you will have to minus VE. Because essentially, well, what I can say is that in this case, the speed has decreased. And so the FC, or the centripetal force, will decrease as well. Now, in this case, we can first put in the 250. And then, however, it's the Earth is rotating or it's spinning the other way, so we have to subtract the effect of Earth's from it. Well, I don't think this way will actually be applicable. Maybe we have to resolve for the speed of the Earth spinning in order to ensure that we have the right answer. Okay, so let's say we have to resolve for VE. Now, in order to resolve for VE, there's one concept. So it's omega is equal to V over R. Now, actually we have to utilize another equation. So from this, omega is equal to 2 pi 1 over t. T for the period. And so then we can plug it in and then find out, or you can say make V the subject. So V in this case will be 2 pi R over T. And so VE, let's say, VE will be equal to 2 pi times 6.37 times 10 to 6 over 1 day, which is 24 times 60 squared. And you can plug this into a calculator. So 2 pi times radius of the Earth over 74 times 60 squared. And it gives us a rather large number. So it's 463, let's round to 3 decimal places in order to be accurate. Okay. Now this will be the speed of Earth, and then we will be able to calculate FC. Okay, so FC will be equal to v squared over r. Now for v squared will be essentially 463.239 minus 250 squared over the radius of Earth, which is this. Now, then we can plug this into a calculator. Oh, 250 squared over 6.7, okay. And it gives us, okay, 0.0714, let's say, newtons. 714 newtons. Now, then we will be able to calculate W2, which is equal to 9.81 minus 0.0, this, so this will be 9.81 minus and 14. Okay, so it's 9.739 newtons. And then now let's see the question. The question wants us to calculate the difference in power weights. Then we'll be able to calculate the difference. So let's say it's W2 minus W1, which is equal to I think I made another mistake. I don't think so. Wait. 9.81 minus, it's 0. Wait a second. Let me do the calculation again. I think I left out another 0, if I'm not wrong. Or else W2 is supposed to be greater than W1. Just hang on with me. Checking my answer. Yes, I left out another 0 over here. Okay, my bad. Okay. So it's 2 zeros. And so this wouldn't be this answer. This should be smaller. Minus 0.00. Okay, so it's 9. Okay. It's 9.803 newtons. And then we will be able to calculate the difference in weight. Which is equal to 0.036 newtons. And this is the answer to the first question. Now for the second question, question 2 says a lead ball is attached to the end of a light metal rod of length L, the other end being attached to a horizontal axle of negligible friction. The rod is given an initial impulse, okay, and swings around in a vertical circle. When it is at the top of the circle, the tension in the rod is 0. What is the tension in the rod at the lowest point of its swing? Okay, so let's look at this question first. Let's draw a diagram first. So let's say this is the axle, and the mass is above it. Let's say the lead ball is over here. Now the lead ball is of mass m. Let's set it as mass m. And now, what is happening right now is that the tangent in the string, in this case, the tangent should be either way. Let's say it this way. T is actually equal to 0. So how does this happen? What is happening right now is that the M is experiencing a force downward. Now the force downward is essentially mg, and apart from that, it's also swinging. So in this case, it's also experiencing another force upward. Now that will be Fc. So in this case, what is happening right now is the equilibrium between the centripetal force and the weight of the lead ball. And what we want to calculate is the tangent in the string when the lead ball is at the lowest point of its swing. And this is the tangent, let's say it's T dash will be equal to what we want to calculate. And over here, what is happening is that it is experiencing two forces downwards. So the first force is mg, however it's experiencing another force which is Fc that is swinging downward, and this is actually greater than Fc. Above it, due to the conservation of energy, the potential energy is converted into kinetic energy. So how do we actually calculate this? The easiest way, I think, is just to establish an equilibrium between Fc and mg over, let's say, this is state 1, this is state 2, and we will be able to calculate its velocity, and we can utilize conservation of energy to calculate the velocity at the lowest point, and then we will be able to calculate its centripetal force at state 2, and then we add up the two forces to give us the tangent. Okay, so first of all, the centripetal force, Fc is equal to mg. Now, what is Fc? Fc, we can say it's v squared over r is equal to mg. Now, what we want is calculate v squared. Now, r is the length of the light metal rod, which is of length L. So let's say it's L mg. So v is equal to the square root of L mg. Now, then we can utilize the conservation of energy. So in this case, its gravitational potential energy is equal to mg times 2L, because essentially this entire distance is 2L, and plus its kinetic energy. And its kinetic energy is Lmg, and then this is equal to the energy at the bottom, and this will be, let's say, it's a half mv squared. V is what we want to calculate, so let's simplify this equation. So it's 2Lmg plus a half Lm squared g. Oh, I made a very big mistake. Okay. The force is mv squared over r. Okay, so the m will be cancelled out, and then what's left would be this. So essentially, this will be a half Lmg. I thought something was wrong, and that was correct. Okay, so let's further simplify this. We can cancel out all the m and time both sides by 2, which gives us this. So it's 4Lg plus Lg. So therefore, V is equal to V is equal to the square root of 5Lg. Now let's look at over here. What we want to calculate now is the Fc at the bottom, and we already know the speed, then we will be able to calculate Fc. Fc will be equal to mv squared over r, which is equal to m 5lg over L. So this will be equal to 5mg. Now, and then the tangent will be equal to mg plus fc, which is equal to 6mg. And this will be the answer to this question.